concentrate on this fusion story. We have a finite abstract simplicity complex and an open set and a closed set complementing each other. And the question is like here, so we have here two such pictures. What happens if we fuse them together? Both spaces have a cohomology, so there are Betty vectors which are attached in each case, and then we can fuse it together. And when we fuse it together, the question is what happens with the cohomology. And what I saw early in January that this is actually, I first thought this is always equal because I looked at geometric examples like this where you have fused two manifolds together, and I saw that the Betty vectors just add up, which makes sense because these are disjoint unions, and which is possible in this framework, this joint union, so the Euler characteristic just adds up. So, but the cohomology, what happens with the cohomology, that's an interesting question. And in this case, like here, if you look at this situation here, so this is 0, 6, 1. This is an open set, and then this is a closed set. If you put them together, we get the whole manifold. And in this case, the Betty numbers really add up nicely. And then I looked at the projective plane, kind of one of my favorite. You see that here, kind of how I had several adventures with the projective plane. It's a very interesting space. It's you take the Möbius strip and you attach a disk. Right? This is a single curve here as the boundary, and then you can attach a disk, and what you get is the projective plane. And the projective plane cannot be realized in three-dimensional space, but there are beautiful implementations like minimizing the Wilmore energy. Maybe I show you a picture of this most beautiful picture of the projective plane, which is also featured in Oberwolfach. By the way, I was working on that time in the 90s on smooth ergodic theory, which also involved projective spaces, but I was in Oberwolfach in 1990, and 91 only this Boy surface appeared. But what happens is when you do that, here we have a Betty vector 0, 0, 1. This is just an open set. It's clear that there should be, should match the Euler characteristic. Of course, Euler characteristic of this open set is 1. 0, 0, 1. Here the Möbius strip is homotopic to the circle. This has Betty numbers 1, 1, 0, like the one-dimensional circle. So there is a cohomology class which winds around, and then when you put it together, then you get the 1, 0, 0. So the volume form here, this area form, has not survived the merge, the fusion. And so what happens is it actually fused together, collided with the one-dimensional cohomology here, and disappeared. And what you have is a 1, 0, 0. So that's the thing. So I saw that it's bigger or equal to 0. I made much more experiments now, kind of with a random simplicial complexes. You cannot look at all simplicial complexes; they grow enormously fast. And but I just take random, maybe with a few hundred simplices, and just see what happens. And what I see is actually something very interesting, that there is always this interaction here always happens as if two particles collide, like one harmonic k plus 1 form and a harmonic k form collide together and disappear. And that's actually already, you don't even have to go to the projective space. You can already do this when you fuse together the boundary of a ball and the open ball to a closed ball. So that's a perfectly fine example. It's actually a very nice example because we understand everything. And so what you have in the one-dimensional case, an open interval, of course, it has the Betty vectors the 0, 1. The length form. There's no zero-dimensional cohomology here. This is a zero-dimensional sphere which has 2 points. Of course, this is 2, 0. That's a simplicity complex. Also, this is a simplicity complex, the complete simplicity complex, which has Betty vector 1, 0. But if you see that when you fuse them together, there is an interaction 1, 1. So there is the 1 form and one of the 0 forms have collided and disappeared. This is a disk, an open disk, and a circle 1, 1, 0, like here. it fuses together to a closed disk, and then you have a 1, 0, 0. Again, we have kind of see that there is a 1 form and a 2 form which collide, and then that's in the, and you take a three-dimensional ball, you have an open ball and a sphere, the boundary, and then there is a 2 form and a 3 form which collide. So these are just examples, and actually if this conjecture here works, that there's always kind of, this is a K form and a K plus 1 form collide, and what we have is, in this case, we have by Poincare duality, we have always a volume form, and it's orientable. If in the orientable case, we have always volume, we have a volume form here, and we have no volume form here. So the volume form cannot disappear, right? This volume form cannot disappear, so there should be no interaction, and you have a fusion identity. So the picture is really kind of, I like to think about this as particles. That's the reason, of course, if you look at the Maxwell equations, in, you know, these are actually one forms. The electromagnetic potential is a one form, and in the vacuum these are harmonic forms. So these ground states, the zero energy, this is always positive. The energy is positive or zero, so the harmonic forms are the zero energy configuration, which are very important in physics all the time, and in this case the harmonic forms are nothing else than cohomology classes. So you can think about these harmonic forms as cohomology classes which kind of live on this basis. So what you have is kind of, in this case, you have cohomology classes. Oh, maybe I should put that here so that there is a closed. So this is a closed. This is a closed set, and there are cohomology classes living here. And then there is a, what happens here? This is an open set, and there are cohomology classes living here. And now when you fuse them together, what happens is they are just, when you apply the heat flow, then they diffuse. That's why fuse is a very nice word. They diffuse under the heat flow to become harmonic forms on the larger space. So then the question is, what happens with them? Do they kind of stay independent particles, or do they collide? And what happens in this case, you see that there's collisions. There's some particles which have lived in the individual spaces have actually collided and disappeared. And the conjecture is that there are no particles which can be created but when you fuse these things together. So the only way that you can create new particles is to add some more space. And so that's the picture. That's a picture which I think is very natural. That's the first thing which came in mind when I looked at that early on. And but this is not proven. But I think it's just linear algebra, because everything we are doing here is basically linear algebra. So these cohomology classes is the null space, the kernel, which we talk about in our linear algebra courses, the numbers here, it's the nullity of some matrices, also something we talk about. The heat flow, that's something we talk about next week in linear algebra. That's actually not next week. Next week we look at discrete dynamical systems. These are continuous dynamical systems here, but you can take t is equal to an integer, and then you get a discrete dynamical system too, and then you have the positive eigenvalues melt away, of course, because this has only positive eigenvalues or zero eigenvalues, and the zero eigenvalues survive, and that's the harmonic forms. So that's the natural thing. That has still to be proven. Okay, that's the status. Maybe I show also something about the, a picture about the experimental data. I just looked at, thousands of simplicial complexes. I look at these vectors, and then I look at all which kind of interactions appear, and then I list them all together and see these are all always, it's always the case that there are these pair annihilations which happen. So I got early acquainted, or high school got acquainted with projective geometry. Roland Sterk, who is actually a grandchild of Hopf, of Heinz Hopf. So because he's a student of Ekman, he was writing some books on descriptive geometry. I've collected once a couple of books on descriptive geometry. It's called Darstellende Geometrie. In German, we had special lectures. So he made special lectures for interested students in the class beyond the usual math classes, and he could kind of really bring across the beauty of perspectives, which is a very, very fancy topic, because if you make photography and the structure of motion, that's another place where I actually then got back into that. So every computer vision story, when you look at different pictures, you'd have a cameras taking different pictures, and you want to reconstruct the object, and you want to reconstruct the position of the cameras. These are data fitting problems which can be solved also with linear algebra. We looked at the 360-degree case, which are actually spherical cameras, which is very interesting with Jose. Also in college, Max Jäger, former high school teacher, he was really great in showing the beauty of projective geometry, and especially also duality, which is everywhere in this in this story. When I was writing my senior thesis, I was very ambitious and wanted to prove a conjecture about the Lyapunov exponents of some smooth dynamical systems like the standard map. And there's an approach which is that you do Le Drapier, that you look, instead of the tangent bundle, you look at the projective bundle, and then if you look at the co-cycle action, you actually look at it on a compact space which has invariant measures, and you look at these invariant measures, which are today called Le Drapier measures. If you would know these measures, you would know the Lyapunov exponents. So that's kind of a place also where projective spaces naturally occur. I work with Barry Tang, who was an undergraduate student here writing a thesis. I advised this thesis. We looked at integral geometry, which is a beautiful topic, like the Buffon needle problem, all kind of beautiful. But it's actually very natural to look at this in projective spaces, because there's a natural invariant measure. If you look at all possible kind of planes, in the affine case, it's a little bit more awkward than in the projective space. And in work with Liz, we looked at kind of more 3D printing. This got me into 3D printing, and actually kind of we printed things in metal. I actually this morning just took this projective plane, the projective plane you find in Oberwolfach, and generated a 3D printable version and submitted it to probably get it in a couple of weeks. Costed maybe $30. So that will be kind of another thing. So 3D printing is not only the actual process, but also the visualization, and that beautiful implementation of this projective plane in the form of this Bryant-Kushner surface is really kind of seen also in Oberwolfach best when you are making it, when you are realizing it not as a surface, but so that you can look through. A story about coloring. There's an interesting open problem, which is when you take a discrete manifold. If you take a discrete manifold and you ask yourself, what is the chromatic number? The four color theorem tells you in the sphere case it's always 4 or 3. Now for other surfaces it's not known. And but when I started working with Jenny, I thought, it might be always 4. In the first meeting, Jenny came and she brought a projective plane. It's a small graph implementing the projective plane, and there the chromatic number was 5. So, but there is no example known where the chromatic number is 6. I have a theorem from last year, 2 years ago, where I proved that the chromatic number is always less or equal to 6 for 2 manifolds. But for the projective plane, there's examples with 5. We don't know whether there's, maybe there is a projective plane where you need 6 colors. I think it is 5, and I think there's a conjecture of Albertson and Stromquist, which they have found examples of tori, where this projective plane is interesting because it doesn't bound a 3-dimensional manifold. It's not the boundary of a 3-dimensional manifold. And I actually thought that brought us to coloring coloring the sphere you can do by coloring the interior, the ball. You color the ball, and coloring the ball can be done by edge refinement within the ball inside, and that's kind of a nice way to color, to maybe also I think it's should be a proof, become a proof of the four color theorem, which is just very intelligent. So what you do is you take a planar graph, put it on a sphere, then you triangulate it completely, make it harder, and then you fill it up, make a three-dimensional story, and then you start coloring the inside. Just make edge refinements so that the inside is four colorable, and that means to get rid of these Fisk manifolds inside. So there should be a linear or quadratic algorithm which colors planar graph. And so that was kind of an exciting project. I mentioned already also there was another place where I got kind of interested more in projective spaces. It was when I was thinking about the Hopf conjecture. The Hopf conjecture tells whether that every even-dimensional manifold, Riemannian manifold of positive curvature, positive Euler characteristic, that's still open, and there is a list of positive curvature manifolds which one believes is a complete list of positive curvature manifolds. I at least believe. And here now the projective plane also is kind of an interesting example to look at. By the way, that also works for high-dimensional projective spaces. If you take a three-dimensional projective plane, what happens is that what happens is if you take an open ball away, you always are getting here something which is homotopic to a sphere, a smaller dimensional sphere. So you know all the cohomology. So in the three-dimensional case, it will be 1, 0, 0, 1, like the three-dimensional sphere, and in 4 dimensions it will be again 1, 0, 0, 0. So because then the rest is again non-orientable. So it depends on whether you have even or odd dimension. But this story is the same for in any dimension. Like here also the story is the same in any dimension. So in these cases we have really always an interaction cohomology. Okay, that's it for today.